Welcome back to another episode of Web3 Smart Contract Security Exploits. If someone sends ETH to your smart contract that you were not expecting, that could actually be a bad thing. I'm going to show you a live attack to demonstrate exactly how the exploit works, but this is only for demonstration purposes, so please do not use this in production code. This is our smart contract, which is a game, and it has one method, which is play. Every person who plays this game has to send one ether. If you're the fifth person to play, then you receive all of the ether from all of the previous users. I'm going to have this user send one ether. By the time they send the 50, it should work. So they basically play the game, they got their money back. All good. Perfect. We have another person who's like, I'm going to rate this game. I don't want anyone to get played and I want them to get frustrated with the smart contract developer. Don't know why they do that, but that's their plan for today. They are going to attack it using their attack method within their smart contract. They are going to send one ETH to the attack method. And then boom, they have now attacked it. But nothing bad has really happened just yet. So let's say other people play this game. So this person just keeps trying. So they play. We're at the fourth play. And then now finally we're at the fifth play. And the payment didn't work. They couldn't even play. Now everybody else is going to send to the smart contract also can't play. Like if they keep trying, like, oh, that should work. Like I'm the fifth person. Let me play. In this exploit, the attacker wasn't able to get any money from the smart contract, but they were able to crash the game. The attacker probably has a similar game, and as a result, they want to crash this one. Everyone else who's trying is saying, yo, like, I'm wasting gas fees trying to play a stupid game. This is nonsense. And they're tweeting all over Twitter saying this is a garbage game. So that's actually a bad situation. Let's explain exactly what the attacker is doing and why that works to attack the smart contract. If we go to the attack method, we have a constructor where we get the victim, we have an owner. This method calls something called self-destruct. Self-destruct is a keyword that is used to completely terminate a contract, remove its bytecode from the Ethereum virtual machine, and any funds that's remaining in the smart contract, they send it to the address that you specify. So as you can see, there's a warning here because this has actually been deprecated. It's only recently been deprecated in February, and the compiler will warn about its use, both in Solidity and in Yule. Even though the compiler warns about its use, you can still get this to work. Maybe in a new build of the Ethereum virtual machine, it won't work. Now, why did sending ETH throw off the logic? The issue is not the fact that they wanted to send ETH to the smart contract. One might argue that receiving ETH unexpected is actually a good thing. It's like digging through your pockets when you're cleaning and you find money. Who wouldn't be happy about that? But in this case, the reason why it's bad is because their logic heavily depends on the balance of the smart contract. In line 21 of the victim code, it says require the address balance to be equal to number of players multiplied by 1 ether. The way how the game works is that all the funds are going to be sent to the person who's the fifth user. So they receive 5 multiplied by 1 ether, which is the cost to play the game. And if the balance is not equal to 5 ether, no money is going to be sent. The real issue is not that it received ether, that it was not expected, but the fact that it depends on the balance of the smart contract to decide whether or not certain functionality works. And that's a bad practice. We know typically when anyone sends ETH to your smart contract, the method receive and fallback can help you process how these transactions work. Let's say you say, if you send money to my smart contract, I'm going to revert and say ETH is not accepted. Let's see if this works. The attack has to happen before we get to 5 players. So I'm going to call attack. And then finally, this is a transaction that will determine whether or not this fix worked. And we can see it failed. And the reason why it failed again would be the same reason: insufficient funds for payout. We're still in a scenario where victim B was able to receive the funds that was sent via the self-destruct method. The thing about self-destruct is that it forcibly sends ETH, so there's no stopping it. And even though it is deprecated, one can argue that maybe they don't have to worry about that in the future. But the thing is, people can find other ways to send ETH to your smart contract. For example, a miner could decide to make your smart contract address the recipient of mining rewards, and that also cannot be stopped. Even though that's a less likely scenario, it still is a scenario nonetheless. So therefore, I highly recommend that you do not depend on the balance of the smart contract to have any kind of tight logic. In the survivor smart contract, the way that we fix this is simply by saying require that the address is at least equal to how much we expect to withdraw and send it. Because at least if we have enough, let's just send it. And then we added a withdraw function, which basically says, okay, well, if we do have excess funds, then send it to the owner. And that way we sort out the scenario of if someone tries to attack the smart contract. So I will demonstrate. I have to keep playing the game. Then I'm going to attack So that attack worked. It now has 2 ETH. And then now I'm just going to keep playing until it gets this situation where it no longer works. And once it has 5 ETH, which should work in our case, and if we do play, it works. We have a balance of 1 ETH. The player is able to get their 5 ETH back. And we're not in a situation where if someone forcibly sends ETH, the entire smart contract logic is broken. And the person who owns a smart contract can also withdraw unexpected funds. Everybody's happy. And in this line here, I hope you notice that I have message.sender is equal to owner. Another way to figure out who sent the transaction is using tx.origin, but tx.origin actually can lead to your smart contract being exploited. If you'd like to learn more about how that exploit works, then check out this video here to make sure that you are writing code as secure as possible. Thank you so much for watching this video and see you in that one. Bye.